Question 9. This question is about pH values. 9.1 for pure water, 40 degrees C, pH 6.67. A student thought the water was acidic. Presumably the student thought the water was acidic because the pH was less than 7, but the pH tells you pH is minus log to the base 10 of hydrogen ion concentration. It doesn't tell you whether something is acid or neutral, or basic or alkaline. If something is neutral, if the H plus concentration and the OH minus concentration are equal, it's only acidic if there's an excess of H plus, and it's only basic or alkali if there's an excess of OH minus. So in water, there's an equal concentration of H plus and OH minus, and that's why it's neutral. So H plus concentration equals OH minus concentration, and the water is neutral. The 6.67 pH is misleading. The 6.67 is minus log to the base 10 of hydrogen ion concentration. So pH is minus log to the base 10 of hydrogen ion concentration equals 6.67. I want to find the H plus concentration from that. So if I inverse both signs, so log 10 of hydrogen ion concentration now equals minus 6.67, and I inverse log minus 6.67, I find out the H plus concentration is 2.138 times 10 to the minus 7. Now Kw, the equilibrium constant for water, always equals the H plus concentration multiplied by the OH minus concentration. That's just something you've got to learn. And since H plus concentration equals OH minus concentration, we can replace OH minus concentration with H plus concentration. So Kw equals H plus concentration squared. We know the H plus concentration, 2.138 times 10 to the minus 7 squared. Kw is 4.57 times 10 to the minus 14. Sodium hydroxide added gradually from a burette 25 centimeters cubed of 0.08 mole propanoic acid at 25 degrees C. I can see that this is a weak acid because it started out at about pH 3 and the pH is only rising slowly. When I get a weak acid and a strong base like sodium hydroxide, I get a buffer here. I'm making a buffer, and that's why it's only rising slowly here. I'm getting a buffering effect here at around about when about 1 centimeter cubed of the sodium hydroxide has been added. It's starting to slow the rise in the pH around about here. I'm getting buffering effect, and then around about here at the equivalence point, pH 7, when both number of moles of propanoic acid and sodium hydroxide are an equal amount at pH 7. After that I get a sharp rise at my equivalence point, when my end point or my equivalence point, and the pH rises very, very quickly up to pH 12. So there's a sharp increase in pH, and that's because I'm adding an excess of sodium hydroxide after pH 7. Now there's something else to note here. Equivalence is when 19.5 centimeter cubed of sodium hydroxide is added. So equivalence at pH 7 is when I've added equal volumes, equal moles rather, of sodium hydroxide and propanoic acid. If I read down from pH 7, I'll find that 19.5 centimeters cubed of sodium hydroxide, that's equivalence when equal numbers of moles of the sodium hydroxide and propanoic acid have been added, and it's pH 7. So at half that value, so when half of 19.5, that's 9.75 centimeters cubed of added. At this point here, 9.75, around about here, around about pH 4.9, at that point something happens. At that point, at half equivalence point at pH 4.9, when half of my sodium hydroxide has been added, then pH equals pKa. So 4.9 equals pKa, which equals minus log to the base 10 of Ka. So 4.9 is minus log to the base 10 of Ka, minus 4.9 is log to the base 10 of Ka. Inverse log of minus 4.9 is 1.26 times 10 to the minus 6, that's the Ka. Suggest which indicator is the most appropriate for the reaction in question 9.2. So at 9.2, there's a large rise in pH in between pH 7 and about pH 11. So there's a sharp rise here between pH 7 and pH 11. shooting right upwards here. So I want an indicator that's going to work in the range 7 to 11, pH 7 to 11. So pH 7 to 11 is 8.2 and 9.8 are between 7 and 11. So cresol phthalate is my answer. The student prepared a buffer solution by adding 0.016 moles of salt Kx to 100 centimetre cube of 0.5 mole per decimetre cube solution of a weak acid HX and mixing thoroughly. So first of all, I've got to recognise my equation. HX is my acid and it's going to break up into H plus and X minus. So Ka, my equilibrium constant for an acid, is H plus concentration multiplied by X minus concentration divided by HX. Now for buffers, if it says buffer, what you do is you cancel the square brackets above and below and turn those into numbers of moles, and you leave the H plus behind. So Ka equals H plus, and you cancel square brackets top and bottom, so H plus concentration multiplied by moles of X minus and moles of HX now. So by getting rid of the concentrations, that's just a trick you can do. Now moles of X minus are the same as Kx, because this Kx, this salt, will break up completely into K plus and X minus. So the number of moles of Kx equals the number of moles of K plus and X minus. It's the X minus I'm interested in. So 0.0136 moles of this salt fully dissociates, fully dissolves in water to make 0.0136 moles of X minus salt. What about my HX concentration? My number of moles of HX here now that I want. Number of moles. Moles is, concentration is moles divided by volume. So moles is my concentration multiplied by my volume. I need to get this in decimetre cube by dividing by 1,000. So small unit value centimetre cubed up into decimetre cube. I divide by 1,000, 0.1. So my concentration is 0.5 equals moles divided by 0.1, which is the volume, multiplied 0.1 by 0.5. 0.05 is my number of moles of HX. So Ka equals H plus concentration multiplied by 0.136, which is my number of moles of X minus, divided by number of moles of HX. And I could calculate H plus at this point and work out pH. Except that they've added something. They've added some potassium hydroxide to the buffer solution. This is the hardest kind of question. So some of these values have changed. So what happens when you add potassium hydroxide to the buffer solution? What actually happens is adding potassium hydroxide alters this. So 3 times 10 to the minus 4 moles of potassium hydroxide, or I could say 0.0003. Moles of potassium hydroxide. What does that do? Well, it reacts away some of the acid, the HX. So it takes away some of the HX. HX is my acid and potassium hydroxide is a base. It reacts away 0.0003 moles of HX. So my HX, instead of being 0.05, it's 0.05, take away 0.0003, which has been reacted away by reacting with the potassium hydroxide. So my new value instead of 0.05 is now 0.0497. And when the acid, the HX, reacts with the potassium hydroxide, it makes salt, it makes X minus. So that goes up by 0.0003 as 0.0003 moles of salt X minus are made. So that goes up to 0.0139. So now my new values, instead of 0.0136 divided by 0.05 are 0.0139 divided by 0.0497. If I rearrange that equation, H plus now comes out as 5.04 times 10 to the minus 5. pH is minus log to the base 10 of that, 4.30. I've put it to 3 significant figures because my other values are 3 significant figures. Okay. A buffer solution has a constant pH even when diluted. Use a mathematical expression to explain this. Okay. Ka, the equilibrium constant, is H plus multiplied by concentration of H plus multiplied by the concentration of X minus divided by concentration of HX. Ka is a constant called the acid dissociation constant, or the equilibrium constant for an acid. So that's constant. Okay. So constant equals H plus multiplied by X minus divided by HX. Yeah. I could rearrange this if I wanted to now. So I could multiply both sides by hx, so my constant multiplied by hx equals h plus multiplied by x minus, and I could divide by x minus, so constant multiplied by hx divided by x minus equals h plus concentration. So, and a buffer solution has a constant pH, so H plus has stayed the same. So, if H plus stays the same, H plus must remain constant, then Hx divided by x minus is a constant. So what you're arriving at is Hx concentration divided by x minus must remain a constant. That is what they're after for a mark.